I'd like to make this process of mathematical induction more formal and do some examples to show you how this process, what the structure of this argument is going to be, and how to use it. Induction is really nice in my opinion because the structure of every mathematical induction argument is very, very, very similar. It's just a little bit of algebra specific to the problem that will be unique, but the structure itself, how you set up, what things you need to have in your proof are always the same. And the conclusion is also always the same. So there's like one conclusion to memorize that will apply to every single possible proof by induction. So we'll state what that is, and then I want to work through a bunch of examples. So the principle of mathematical induction looks as this. It says, suppose a proposition is defined for every integer n is greater than some starting value a. Often a is 1, but it can be any. It can be any whole number, positive or negative or otherwise. It doesn't really matter. But it depends on your statement, what you're trying to prove. Okay. So if that's true, then this is the principle of the mathematical induction. This is also going to be the conclusion of every proof by induction. You'll just replace the initial if with since. But we'll see that in a second. So then, and the claim is this: if the basis step is true, and we'll talk about what a basis is in just a minute, is true, and I'm going to use the letter M. If the M plus first step is true whenever the M step is true, then the proposition itself is true by the principle of mathematical induction. For all n greater than or equal to. So this is the domino effect I talked about in the previous video. So the idea of what we're going to do is we're going to show that our formula or our statement works for a basic case, or basis is what it's called. And then we're going to show that every time we're at a step, that step means that the next step, or then plus first step, is also going to work. So we're like knocking over, every time you're at a step, you knock over the next step to make that true. And then that knocks over the following step, and so on and so forth. And this just goes on infinitely along for any point down the line. Okay. So proofs by induction have this basic structure. We always start a proof by induction by stating what the basis is and showing that this basic case is true. If you recall, these are some conjectures from the previous video. We want to show that the sum of the first n terms of this sum always adds up to our conjecture, and if memory serves, we want to show that this adds up to n squared. And this is for n greater than or equal to 1. Okay, so how do we do it? Well, first step, step 1 is we need a basis. This is usually the easiest part, and this is at least 1, if not 2 points of any proof by induction you'll be asked for on an IB exam. In this case, the basis step is the first step, because n is 1, so we'll look at that case. That is, we think the sum should be 1 squared, which is 1. And by plugging it into our formula, which says that this should be equal to 2 times 1 minus 1, because it's the first case, plug in 1. 2 times 1 is 2, 2 minus 1 is 1. 1 equals 1, the basis holds. Okay. The next is called the inductive hypothesis. In this step, we're gonna assume that this works up until a point, and we're gonna show that if it works up to a point, then it's gonna work for the next point. So we're gonna suppose the statement is true up until a given point. So we're gonna say suppose this sum, which in sigma notation is k equals 1 to n of 2k minus 1. Suppose this statement is true for the first certain number of cases, and this is where I like to use, I'm going to use a letter that's a symbol that's not the index and not the original ending term. So like often n is in the formula, so I'm going to use like a letter close to like m, but it doesn't really matter. But I'm going to use m. It's true for the first m cases. So we're assuming that this formula works up until a point. The point happens to be m. And now what we need to show is we need to show that if it's true up to this point, then the next case will also work. So how do we do that? We're gonna assume it works for the first m cases, and now we're gonna examine the next case, or the m plus first case. What is the m plus first case? That's this sum, but instead of ending at m, it ends at m plus 1. So the m plus first case is sum from k equals 1 to m plus 1 to k minus 1. And what we need to show is we need to show that we need to be able to rearrange this formula, knowing what we know about this formula. We need to rearrange this, and we'd like to show that this is equal to what we get when we plug in m plus 1 in for n into this formula. Okay. What we do not know, and what you should never ever write down, is this is just flat wrong. It's logically not true. Is you should never just fill in m plus 1 on both sides of this equation immediately. Never ever ever do that. I see that a lot. It's bad. It's not only bad form, it is incorrect. Do not do it. What you should do is fill in on one side, and we're going to work our way through some implications, some algebra, and show that in the end we get what we would get if we plugged in m plus 1. So we're going to start on the left side, show some steps, show some algebra along the way, and then we're going to end with equals m plus 1 squared is what we want to do. And we're going to do that. It's not that bad. So here's some common things we're going to see. Note that this sum is equal to, if we were to sum to m and then add in the m plus first term. So I think this is the same as if I sum the first m of these. And then I added on whatever what the final term would be. And that would be what I get when I plug in m plus 1 into my summation formula. Plus 2 times m plus 1 minus 1. This is, maybe to make it a little clearer, this is the first m terms, and this is the m plus first term in this sum. And when I put these together, I would have gotten this full sigma notation with all the way to n plus 1. So how do we deal with this? Well, this is nice. This actually works out well because by the inductive hypothesis, we know what this is equal to. We have a formula for, we know how the first m of these behave. We just don't know what happens when we add one more to it. We know how the first m of these behave, and it behaves according to our hypothesis. It behaves according to our hypothesis. So if we sum to m, this would be m squared, because this first sum is m squared. And then we're tacking on a 2 times m plus 1 minus 1. because that is the n plus first term. So if I maybe do a little distributing while I'm here, 2 times m is 2m, 2 times 1 is 2, 2 minus 1 is 1. Again, I just distributed here to come up with 2m minus 1. And, well, what do you know? This actually factors. This factors to m. Oh, sorry, that's not a minus, that's a plus. Yeah, 2 minus 1 is plus 1. This factors to m plus 1 squared. So what have we shown? We've shown that we took the m plus first term, we peeled off the term we added on so that we could have an expression that matches our inductive hypothesis. We took out this crazy sum and replaced we replaced what we assume this sum adds, the formula for the sum actually is, to get an easier to work with term. We added in the next term to make the m plus first case, and then we recognize this as this factors to, looks like in this case n plus 1 squared, which is what we hope it would be if we replaced the n in the beginning with an n plus 1. So what we didn't do is we didn't just plug n plus 1 in both here. We started on the left side and showed that it results in the right side. This is exactly what we're trying to do. This is our conclusion. Every proof by induction ends with a statement of that this was true because of mathematical induction, and it is exactly, as I mentioned at the beginning, it's going to be exactly this last sentence we wrote in mathematical induction, but replacing the then if with since. So the final step of this proof to finish this off is since the basis is true and the m plus first step is true whenever the m step is true, the proposition is true by the principle of mathematical induction for all n greater than or equal to our starting value, which in this case is 1. So just to recap, every proof by induction, no matter what you're trying to do, is always going to have these. These components: a basis component, an inductive hypothesis component with this statement. You're going to examine the n plus first case. This is where this algebra specific to the problem will be used, and then it always ends with the same conclusion. So, long story short, if you're taking the IB exam, or you're on, say, one of the tests or midterms for this class, and I ask you to prove something by induction, then your problem should definitely have all of these components. And if you include all of these components, you're going to get most of the credit for the problem, even if you don't do the algebra in the middle that's specific to the problem correctly. You're going to be guaranteed to get a majority of the points. So even if you're not sure how to do the algebra itself, knowing the structure of a proof by induction will get you in a good spot. I'd like to do one more proof on this video, and then I'll take a quick break, and I'll do a few more examples, but I'll edit that into a second video. A pretty common proof by induction that we're going to see is divisibility proofs. If you recall from our conjectures, we conjectured that 11 to the n minus 1 is divisible by 10. I'd like to show you how to use induction to prove this. Just as we did in the first example, we're going to start with a basis. And the basis in this case is that 11 to the 1 minus 1 is divisible by 10. And this is 11 minus 1, which equals 10. And 10 is clearly divisible by itself. So the basis holds. Now the inductive hypothesis. Is suppose 11 to the n minus 1 is divisible by 10 for the first m integers, or up until m. So now, what we'd like to do is now examine what does 11 to the m plus 1 means. Well, before we get into that, though, for divisibility proofs specifically, which are a common proof that you're going to see multiple times, is that for divisibility proofs, we'd like to explore a little bit further what it means to be divisible by this number, and we're going to come up with an equation that's going to be useful for us to use. Specifically, what I'm going to tack onto this is what this means. Is 11 to the m minus 1 is, if it's divisible by 10, that means we should be able to factor a 10 out of whatever this number is, or specifically this is equal to 10 times something, and I'm going to represent that something with an a. So if you're divisible by 10, that means that you should be equal to 10 times some number, and this is going to be pretty useful for us in the algebra part of our proof in a second. Okay, so here's our inductive hypothesis. Now we're going to examine the m plus first case. Okay, the m plus first case is we're going to look at numbers of the form 11 to the m plus 1 minus 1. So this isn't as straightforward as the previous one where I just like peel off a term. It's not exactly there. Because like everything's not multiplied by 11 to the m, but we can do something similar in that exponent rules tell me that 11 to an exponent that's addition into it, or a base to an exponent with an addition in it, means that I should be able to split this, rewrite this addition as 11 to the first power times 11 to the m power. So I split this using exponent rules into the base to the first power times the base to the m power. This is where this equation that we came up with by divisibility is going to come into play, because 11 in here I see there's an 11 to the m term. So I could rewrite this as 11 to the m is equal to 10 times something plus 1. And this is where the inductive hypothesis is going to come in. So by the inductive hypothesis, this is equal to 11 times, not 11 to the m, but 10a plus 1 minus 1. What is this? Well, if I distribute 11 in here, this is 11 times 10 times a is the first term. Great. 11 times 1 is 11 minus 1, which is 11 times 10a plus 10. This is clearly divisible by 10 because each term is divisible by 10. If it's not, if you want to be even more precise, you could factor the 10 out. This is equal to 10 times 11, not h, 11a plus 1, which is, since 10 is a factor, it's clearly divisible by 10. So what we've shown is that assuming that the previous step is true, then the next step we worked our way through and showed that this expression is definitely divisible by 10. The only thing left is to write the conclusion, which is this again the same for every proof by induction. Since the basis is true and the m plus first step is true whenever the m step is true, the proposition is true by the principle of mathematical induction for all n greater than or equal to 1.